And all right, cool. Jim, I
Hey
will just
guys,
yeah.
welcome to our first application workshop. So today, me and Anish are going to be talking about feature engineering and representation learning, which is essentially where you take your features and kind of transform it into um, a, a feature space or like a representation that is kind of better for your model to process. And there's a lot of benefits of this. It can improve the accuracy of your model. It can speed up your model. And yeah, so let's get started. So this is just a brief overview of what we're going to be going over. So first, we're going to be talking about what feature engineering actually is. And then we're just going to do kind of a broad overview of techniques for different subsets or different subcategories of feature engineering. So this is meant as kind of just like a broad introduction of what techniques are available to you. So we're not going to go like too much into the math behind everything. But after this, you should get, a decent idea of kind of what happens like before you input your features into the model and what kind of processing you need to do. Yeah, so feature engineering is essentially turning raw data into features. So oftentimes the raw data that you get when you're doing machine learning is not really in like a friendly format to be able to just directly input into your model. So examples can be like words or like just random things that are not kind of numerical or don't have a good numerical structure. Because most models, work with numerical data. And then, so yeah, good feature representations would simplify the models and improve
Can you see the
performance.
signs of do not
So
disturb?
you're gonna,
No, I'm in a
did someone say
class.
something?
He's good.
Um, yeah, so you're gonna see examples where if you have a better feature representation, it's gonna make the model like a lot faster to learn. And it's also like in a lot of cases, some models that can't be learned with simpler features can be learned with transformed features. So the subproblems are listed here. So first we're gonna talk about how you represent raw data in the first place. So like when I talked about like words and stuff like that, how do you represent words and feed words into your model? The second one is gonna be feature generation. So this is like how you take some features and create new features in the hope of, making a model able to fit more data or like fit the data better. Then we're gonna be talking about feature selection. And this is kind of where like the simpler models thing comes into play. And then we're going to be talking about feature extraction, which again helps simplify your model and also in many cases helps improve performance. So before we move on, does anyone have any questions?
I didn't understand what feature selection exactly meant. Like we usually said it to simplify. In what sense?
Sure. So we're going to be talking about that more later, but essentially you can think of feature selection as taking the features from your feature set that most represent the outcome. So you have some inputs and you have some outputs, and you want to choose the inputs that best allow you to predict the outputs. So
Okay.
like the benefit of this would be like if you have a bunch of data, but like 90% of it just does not matter at all, then you don't want to feed all that data into your network. So you want to perform some kind of like statistical test or something to determine which ones you actually want and which ones you just want to throw away.
Makes
Make
sense.
sense?
Yeah. Thank you.
Any other questions? And if you have questions, you could also just type them in chat and then I'll go over them like once I'm done with the slide. Yeah, so raw data representation, a lot of these techniques are generally dealing with categorical variables. So you can imagine if your data includes categories, then it's kind of not easy to directly input them into your model because like models generally don't work with strings and stuff. Um, so one, oh yeah, and categorical variables, they're not necessarily like non-numerical, right? They could contain numbers. So for example, like zip codes or even ordinal categorical variables. So like if you, I don't know, if you ask a bunch of people to like rate a movie on a scale of 1 to 5, then a lot of the times you'd process their rating as actually a categorical variable instead of a numerical variable, just because it's not kind of defined in a numerical space and like arithmetic operations aren't defined on it. So yeah, generally, if your variable lives in a space where you kind of can't perform arithmetic on it, then you would count that as a categorical variable, and then you would use these techniques to deal with it. So yeah, the most common technique for dealing with categorical variables, and also the simplest, is one-hot encoding. So you can see on the right an example of this. So essentially, you would take like a bunch of categories and then assign IDs to them. And then for each of your data points, you would create a vector where each one is, or sorry, these IDs are actually the IDs of your data points. But each like position in the vector for your data point would consist of a 1 if it matches that categorical variable, and a 0 if it doesn't match that. So for example, if you have like 4 things, one is red, one is blue, one is green, one is blue, then you would map each of them into a vector of 3 elements, because there's 3 different colors, red, blue, and green. And then each like position in your vector would correspond to whether or not that color is like the color of your data point. So one really good thing about one-hot encoding is that it's really good for linear models. So the reason for this is that let's say you have some kind of alternative encoding where you just map kind of red, blue, and green to numbers, right? So let's say red is 1, blue is 2, and then green is 3. But the downside for this is that when you're using something like a linear model, it can't really, it would, like a linear model would assume that there's some kind of ordering, like a natural ordering, right? So it would map, like, for example, a higher number to 2 than to 1, and a higher number to 3 than to 2. But if your data set kind of doesn't define that natural ordering, so there's no like meaning in saying that red is greater than blue is greater than green. So in that case, like linear models would perform really poorly. So you want to use one-hot encoding, and that can perform like a lot better. One downside to this though is that it increases the dimensionality. So if you think of like natural language processing, where you're kind of processing words that can come from like a 5,000 word dictionary, then each of your vectors, if you're just doing one word at a time, each of your vectors is going to have a dimensionality of 5,000. So that would be really bad, right? And one way we can deal with this is kind of merge rare categories into like an other category. So for example, if you have a bunch of words in your 5,000 word dictionary that are basically never seen in like regular text, then you could just lump them all into one category. And that would, like in a lot of cases, it would decrease the accuracy of your model, but it also just like would make your model like exponentially easier to train. So in a lot of cases, that can be a good idea. And then one example of like how one-hot encoding can generalize to you know, multiple different encoding methods is bag of words. So bag of words is really popular in NLP as kind of just a baseline encoding method. So like in practice, people usually use more sophisticated embeddings like Word2Vec or like BERT, stuff like that like Google recently came up with. But like if you just want a baseline that's really simple to train, you can use a lot of variations of one-hot encoding. So bag of words in particular is like, instead of processing one word at a time, if you want to process like a series of words, like if you want to process one sentence at a time or a paragraph or even a document at a time, then instead of storing like whether or not that word is present, you would store a count of the word. So you can see an example in the right, like bats can see via echolocation, see the bat sight sneeze. So in here, at occurs 0 times, bat occurs twice, can occurs once, and so on. So that's how you would encode that. And in practice, this actually, like bag of words actually performs decently. So that just shows you that like very simple encoding methods, like one-hot encoding and its variations, can actually give you a pretty good baseline to kind of test your like more complicated encoding methods that you want to try. And yeah, there's also definitely downsides to this. So one downside to bag of words would be that it loses the ordering information, right? So if you say like fly bats or bats fly, it would have the exact same vector. And that's kind of a downside. But like even with that downside, it still generally performs okay. Any questions? All right, next slide. Yeah. So like Alexi said, like one kind of problem with it is that it's really sparse, and usually you don't want like vectors that are super sparse, because you would want to transform it into a kind of denser vector that is more like compact. So now we're going to talk about like raw data representation. So sometimes you have numerical variables that you can kind of.
Oops, my bad. I'm so sorry. I had a question. So
Yeah,
you
go ahead.
that the vector becomes really sparse. How is that?
Yeah.
How is that kind of different from having just a really big vector? It's the same point, right? That you're making here.
Yeah, I
What do you mean? So
Because
yeah, Alexi, go ahead.
Yeah, I think it's just like sparse, I guess, means there's a lot of zeros in the vector, right? It makes like the model like has a really hard time like finding a signal for every for like finding a reasonable signal for every input. Like since a lot like if 99% of like your input vector is zeros, it might not like just not never be able to train like really good weights
Oh,
to be able to perform well.
right. That
Yeah.
makes sense.
Yeah,
Yeah,
and
just
that
having
also
like go ahead.
oh wait, were you gonna say something?
I was just gonna say like in practice is just having like a lot of really sparse data is just ends up being really bad.
Yeah. And it also kind of relates to this thing that is called the curse of dimensionality, which is, you know, a pretty big problem in a lot of machine learning models, where if you have like more dimensions in your data, then you need like an exponential number of data points to be able to accurately represent all your dimensions. So like if you have like a really, like Alexi said, if you have a really sparse vector, then you're gonna need a lot of data points where kind of each like position, each element in the vector has something in it. And because of that, you're just going to need like a lot more data in order to train like an accurate model. So that's often a problem that we have to deal with. Yeah. Okay, so yeah, now we're going to talk about raw data representation in terms of numerical variables. So like, let's say that you have these numbers that you can directly input into your model, but the numbers kind of like look weird, right? Like if you plot the numbers, maybe they look extremely skewed. If you have skewed data, then it's kind of not going to work with a lot of simpler models. So if you think about, for example, linear models, if you have a lot of skewed data, then you don't necessarily want to directly just input that. So one way that we can deal with skewed data is that we can transform kind of the values in the data. So for example, if you look on the right, there's the original data set, which looks really skewed. But if you take the log of that data set, then it has a lot more a normal distribution to it. So if you kind of map your numerical variables and give them a normal distribution, then oftentimes in practice, it's going to perform a lot better with a lot simpler models. Another example is the Box-Cox transform, which is basically the same thing, except it uses power functions. Yeah, and another way of processing numerical variables is, okay, I'll answer the questions after this slide, but is you can do binning, which is basically you group continuous values into bins and kind of like represent them categorically. So like, why would you want to turn numerical variables into categories? So in a lot of cases, like your numerical variables, the point of processing them is that, you know, you can define arithmetic on them and they're kind of a natural thing to work with, right? But in some cases, they could be numerical and they could be like, they could be amenable to arithmetic. But there's kind of also a very natural way of grouping them into categories. So for example, if you were thinking of like latitude and longitude, then it could be natural to kind of group it into, I don't know, like the North Pole, and then kind of like the North America section, like above the equator, but below the North Pole, and then like below that, and then the South Pole after that. So like if you can group your numerical variables into categories that all generally share like the same characteristic, then it might be a good idea to use binning. And another good thing about binning is that just like statistical transformations, it also allows you to kind of make the data more normal. So like if you have the raw data on the left, it's very skewed, but then if you kind of use, this would be adaptive binning, where you basically split the data into quantiles and then you say, okay, I want 10 bins. Then you take like the first 10% of the data, put it into one bin, the second 10% put it into another bin, and so on. And then that just kind of equalizes your data so that you have like an equal number of points for each category, which can oftentimes be a positive, you know, benefit for your model. Yeah, so it's not necessarily only useful for linear models. So there's like, whenever you're processing numbers, basically, it's generally just a lot better to work with uniform or you know, normally distributed data than it is to work with very skewed data. And there's a lot of like statistical reasons for this that I won't really go into. But yeah, just know that that's the case. Of course, if you have really, really complicated, like really dense neural networks, then in the end, it's probably not going to matter just because you're transforming the data like in between so much But if you have kind of simpler models, then it's often, even if it's not a linear model, it's often a good idea to transform your data. Yeah, so adaptive binning would just be to use the distribution to decide what your ranges of your bin are. Yeah, so now we're going to talk about feature generation. So this is kind of a different problem from feature representation. So basically here, kind of going contrary to what you would expect, you would actually want to expand the feature space. So oftentimes, if you create new features by combining or transforming existing features, it can make like really simple models or like really easy to code models actually capture very, very complicated kind of decision spaces or complicated models of the data. So what like a visualization of this transformation would be that you have your input space. So maybe it's a 2-dimensional input space that just contains an X and a Y coordinate. And then you take some function, let's call it phi, and then you transform each of your points into 3 dimensions. So you create a new feature based on some combination of your existing features that you also add to your feature vector. And by mapping it into 3 dimensions, you can see that now there's a hyperplane that separates the points. And you no longer have to like learn this kind of twisted, weird like transformation in order to map a decision boundary between the blue and the red points. So yeah, the purpose of this is kind of just mapping to a higher dimensional feature space to allow your data to, be separated. So like I said before, this allows very simple models to model complex relationships. So for example, you guys learned about linear and logistic regression, right, in your fundamental series. So like if you were doing like logistic regression, then if you have like a feature space like XY, then logistic regression can only map a linear boundary, a linear decision boundary, right? So if you look at this, like where your decision boundary is kind of circular, where like inside the circle, you would want the blue points, and then outside of the circle, you want the orange points. Then if you just use naive logistic regression, then it's only going to map a line. So any line that you fit to that is going to perform really poorly. But if we just transform the feature space, so I think you can like, yeah. So if we just transform the feature space from XY into like X comma Y comma X squared, Y squared, XY, and 1, then using this, we can map any like polynomial function or any like degree 2 function in 2 variables to our decision, or our decision boundary can consist of any polynomial any degree 2 dimension 2 degree 2 function basically. So if you were to imagine like, I don't know, an ellipse or something, then it could learn that. Or if your data is maybe separable by a hyperbola or something, it can also learn that. So yeah, the plus side of this is if you want to use a really simple, just like linear model, but you want to model complex behaviors, then you would want to expand your feature space. But a really big downside to this is that if you expand your feature space too much, then it can result in overfitting. So like one very common way to expand your feature space is to introduce polynomial features. So for example, if you're just given a feature X and you want to produce an output Y, then maybe a line doesn't fit. So you want to introduce features like X squared, X cubed, X to the 4th, and so on. And if you have like a function that maps, like if you have a function that's, 1-to-1, then it maps like every single X to a different Y, right? So actually, if you had a high dimensional polynomial, then you could actually fit any function to that data set, right? As long as your data set doesn't contain like duplicate X values with different Y values. So based on that, like we can basically achieve 100% accuracy on your data set if we include like 1,000 like a 1,000 degree polynomial, right? But the downside to this is that it can result in overfitting. So if you look at the picture on the right, like you're kind of mapping this, I don't know, like 15 degree polynomial to this thing that looks like it should just be a straight line. So if you were running this on your test data and you try to classify like a point in the middle, like for example, between the first 2 points, then it's going to perform really badly. So you have to watch out for overfitting and for not like introducing too many features. Any questions?
Yeah, like this slide is very important, or this concept is very important. So if there is anything that's kind of confusing, be sure to ask questions. Because
Yeah.
like the ability to kind of use simple linear models to model very complicated things is like very powerful, because our understanding of linear models goes way more, like goes way beyond our understanding of very complicated models. So being able to kind of dissolve or reduce the inherent modeling into something that we're familiar with is like really, really powerful.
But why is it, one second, I'm kind of confused as to why it's so important that we use linear models.
It's not, so it's important because, well, it depends on the use case, of course, but linear models are just inherently interpretable. Like we can actually take out the weights of linear models and see which features are the most important. Whereas in very complicated ones like neural networks, it's very difficult to kind of understand what the model is doing. So you're absolutely right that like nonlinear models, like neural networks and such, are very powerful in their ability to model very complicated things. But linear models are really cool because you actually have some level of interpretation of what's going on.
Yeah, I think overall, like there's a couple of like different features you can look at for like that linear models have that neural networks don't. Things like outliers, just being able to scale your computation, like linear models, or like just specifically in linear regression, it's just a closed form like solution. I think there's also like there's a couple of different like studies that have shown that like neural networks don't really deal well with irrelevant inputs. Like if you're just feeding it noise, that might really affect it. Overall, like neural networks, and this is like a very high level explanation, but they just have like a lot of variance. A slight change in your input might result in like a drastic change in the output, and that's just like that's not necessarily a feature you want to have, and like that's something that linear models just don't.
Yeah. So for like interpretability, simplicity, and oftentimes it just, like Alexi said, performs better than neural networks. Linear models are definitely a good idea to know about. And yeah, I think like in practice, like a lot of people nowadays just like slap a neural network to everything. But honestly, that is often not a really good idea. So like a lot of like a common thing that people do in practice too is first fit a linear model to kind of make sense of the data and see what the baseline would be, and kind of just figure out like how the data is, like what the patterns between the data are, and then you try like more sophisticated features on top of that. So yeah, it's definitely a good idea to know about linear models and to use them in practice.
If you take 189 at some point in college, you'll actually get to experience kind of the analysis behind a lot of the linear models. Like it turns out that you can actually do a lot as a scientist when you have a data set and analyzing like singular values or just like random like mathematical properties of your data or your model. And it turns out linear models actually can be used very specific and very with well-intentioned ways to really do whatever you're trying to do. But obviously that's like a whole thing. So definitely take the class if you're more interested in that kind of stuff. But the whole point of this is just to show that like when you can, always try to reduce the complexity of your model by generating more features. And it's always something to just keep in the back of your head.
Mm-hmm.
Cool.
Okay.
Any more questions? Sweet.
All right, so now we're going to talk about feature selection. So the point of this is to reduce the number of features by selecting only those that are most informative. So like I said before, there's the curse of dimensionality, where if you have like a really high dimensional feature space with a lot of features, then you're going to need an exponential, the amount of data that you need to train your model will exponentially grow with the dimensionality of your data set. So in order to avoid this problem, we want to select the features in our data that are most representative of the outcome. So this could like reduce our feature set of like 1,000 to maybe like 100 or even like 10. So yeah, this improves the model efficiency, and it also drastically reduces the risk of overfitting. So like Alexi mentioned before, if you have a lot of noise, just like a lot of data points or a lot of features that are just noisy, and you try to map kind of a complex model to it, like a neural network, then it's gonna like overfit to that noisy data, and it's just gonna learn patterns that have nothing to do with how the data is actually distributed. And that's bad, right? So in order to reduce that, you want to make your model simpler so that it doesn't deal with that many features and it just learns what's important. So in terms of feature selection, there's kind of three subcategories. There's filter methods, wrapper methods, and embedded methods. And we're going to talk about each of these individually. So if you have questions about like any of those, hold off on them. But any questions about why we do feature selection? Okay, next slide. So first we have our filter methods. So I'd say this is kind of the most obvious thing that you would think of when you just think of feature selection. So basically you would perform various, statistical tests that show how each of your feature variables correlates with your outcome. So yeah, you can, yeah. So there's a lot of like different statistical tests that you can use for different situations. So for example, if your output and input are both numerical, then you can use something called the Pearson correlation coefficient, which basically like outputs a number from 0 to 1, something like that. That if it's a higher number, then that means that there's more correlation in your data between those two variables. If it's a lower number, then that means the variables aren't very correlated. Of course, this is just measuring like simple like linear correlation. But like we said before, just the linear correlation of your variables can actually be very powerful to look at. So yeah.
Wait, actually,
if you have
it's a negative 1 to 1, right?
Okay, yeah, that sounds right. Yeah. So -1 would be like a negative correlation, 0 would be no correlation, and then 1 would be positive. So numerical input, categorical output, you could also do that. That would be ANOVA. I think there's another, oh, never mind. Yeah, so you could use like ANOVA for that situation. And that basically does the same thing. It just kind of tells you like how yeah, AP SAS. Honestly, I don't remember this stuff at all, but like, they're techniques that you can use, so awesome. Yeah, so ANOVA basically just does the exact same thing. It tells you like how much your numerical input, like how much a variation in your numerical input is gonna explain a variation in your categorical output. And if you have categorical input and categorical output, then you can use chi-squared, which a lot of you may have heard of if you took AP Stats. Honestly, like I don't remember that at all. So like don't ask me too many like detailed statistical questions on it. But yeah, and then another thing that is actually very powerful, I think you can also use it with numerical data, is mutual information. So this is used a lot in stuff like decision trees, where it just tells you like, basically, if you take like one variable, how much information does that give you on the rest of your variables? So like, for example, if you were training a decision tree to like split like things into categories, then you can say like, if I have information on this variable, then how much does it allow me to actually split up the remaining variables, and like how powerful is that variable basically? So mutual information is a very powerful tool that like people use very often. Any questions on this slide? Okay, moving on. So a second kind of subcategory of feature selection is wrapper methods. So the idea here is that you want to create models with a subset of your features and just run it through the model and see what works better. So this, you can select features with a kind of simpler model than what you're using, like as your final model. So like if you're using a neural network as your final model, maybe you just want to use a decision tree or a linear model to perform wrapper selection and to select the potential features that you're going to input in the end. So you can see the visual that kind of describes the pipeline of this. So you take your entire data set of features, or your entire feature space, and then you reduce it into a potential set of features. So maybe you take like 3 at random out of them, and then you evaluate that. And then you kind of calibrate the model to like make sure that your model is actually like doing what it's supposed to, and then you repeat. So by doing this, you can kind of measure which features worked better which features work better to evaluate the outcome, and then you can use like those features that work better in your final model. And the reason that you might use this instead of the filter methods that we talked about is like, maybe you have like a slightly complicated relationship where the outcome actually depends on a joint of like 2 different features, but like each of these features doesn't really provide information on its own. So for example, if you're thinking about XOR, the function XOR, then like if you have true or false as one of your variables, that would provide you no information on the outcome. It's still 50-50 true or false. But if you have two variables, then that can provide perfect information on the outcome. So in that case, you might want to use a wrapper method where you kind of test a subset of variables and see like what works better. So one specific like technique for wrapper methods is recursive feature elimination. So that's just like what I talked about before. You train model with your features, and then you use some kind of statistical method to obtain the importance of each feature to your final outcome of the model. And then you just eliminate the least important features. And then you repeat that until you have a good feature set that you're satisfied with.
Any
Does
questions?
anyone have any questions?
Yeah.
Wait, specifically, like, doesn't this feel like just filtering but iterative, where like you're just filtering one at a time? Like, is there a major difference between the two?
Yeah. So if you just perform like a statistical test on two variables, right? So let's say that you have like a set of X and then a single Y, right? So if you just perform a statistical test on one of the X's and how it correlates with Y, then you might get zero correlation, right? But that doesn't necessarily mean that X has nothing to do with Y. So like I mentioned before, let's say you have X1, X2, and then they're like Boolean variables, and then Y equals X1, XOR, X2, right? So if you just try to correlate X1 with Y, then like if you know information about X1, that's going to give you zero information. Oh yeah, thanks Alexi. That's going to give you zero information about Y, because like if X1 is true, then Y has a 50% chance of being true and a 50% chance of being false. But if X1 is false, then Y also has a 50% chance of being true and a 50% chance of being false. But if you use something like wrapper selection, then you're testing a lot of features at a time. So maybe like that one feature alone doesn't give you anything, but that one feature combined with another feature can give you a very powerful representation of the final data. So in cases like that, like you would want to test like how multiple features inputted into your model can affect the outcome. So yeah, it's like, it's less simple than filter methods, but it often works a lot better. Does that make sense?
Mm-hmm. Yeah, so it's sort of like arbitrarily like removing features and then like seeing how good it is. Is that what it is, sort of?
Yeah, sometimes it's like that. But recursive feature elimination, what this does specifically is that, let's say you have like 5 features, you run your 5 features through your model, and then you kind of like use the outcome and see which feature which feature, like after you inputted it into your model, which feature helped explain the outcome the least, and then you take out that feature. So that's also like a little bit different from filter methods, because like it's not just measuring the direct correlation between that variable and the outcome. It's kind of measuring like how that variable through your model affected the outcome.
Yeah.
So there's still
I think
Yeah,
just to like reiterate, I think what Jim like Jim was saying, the importance of each feature here is not like is not from like a statistical test, but it's like some models you can you can get the importance of some features like specifically just by training a model. Like if you, I guess when you learn about decision trees, you'll find out that like, oh, you can look at how many like, or how often this feature was used to like make a new branch, or cause a new split in your tree, which like with which you can like see how important it was to predict your outcome. So like I guess the importance of each feature you're getting here can be like from training your model rather than doing some like really simple like statistical test.
Yeah, exactly. Does that make sense?
Yeah.
Cool.
So wait,
any more questions?
yeah, if I'm like, a very simplified way that I'm trying to understand this is basically we're training the model, and this is just simplified. Yeah, if it's like if we train the model without using that feature, and then we kind of see how that performs against having that feature, and then seeing whether or not it makes a big difference, and then accordingly eliminating. Is that kind of what we're doing?
Yeah, that's basically what we're doing. I mean, there's a very subtle difference here. It's like what Alexi said, you're actually like using that feature in your model and just determining, like directly determining how that feature like did in your model. So like you don't necessarily like evaluate that against removing the feature, but you just like directly just see how much it affected your outcome.
Like the important point is that we actually train the model again and again.
Yeah, exactly. So you train a simple model and see what works best, basically. So you're right. Yeah. All right, next slide. Okay, so this is the final kind of subcategory of feature selection. You have embedded methods. So this is where kind of feature selection is just directly built into the model. So you, well, it might still be a good idea to perform other feature selection, but like your model itself already helps you to select features. So one example of this is L1 regularization, which if you don't know what that is, it basically penalizes the weights of your model in like a linear fashion. So it encourages some of the weights to go to 0. So the way this selects features is that if you have a lot of like non-zero weights or like positive weights, then you're gonna you're gonna have some kind of loss for that. So that's gonna be suboptimal. So maybe it's better to shrink those weights to 0 and then make the features associated with that weights basically not matter. So that way those features are kind of eliminated from the model. And then you often end up with a model that can generalize a lot better. So it helps like drastically reduce the risk of overfitting. Yeah, and then next kind of method for embedded feature selection is random forests or decision trees. So this, like, if you ever take like 188 or something, you'll learn about how like in random forests and decision trees, you just automatically discard features with what we call a low information gain. So if you see that like, so this is implicitly built into the model where like, if you kind of split a decision into 2 branches, but as a result of that split, you didn't gain much information, then you just kind of prune that split and you don't use, you know, the feature that created that split. So yeah, stuff like L1 regularization in like linear models or random forests and decision trees, those have feature selection directly built into them. And that can often be a good idea to you know, prevent overfitting and just simplify your model a lot.
Alexi, I think we're going to go over random forests and decision trees at some point, right?
Yeah.
Yeah, cool.
Yeah, okay, cool. PCA and other dimensionality reduction methods are actually our next topic. So
actually, even just before that, I guess one thing I wanted to mention with this whole feature selection concept is that like you have to make sure that like as you're kind of evaluating different subsets of features, that ultimately when you evaluate your model, you ensure that you only evaluate it on a test set once, like on a completely separate test set, because something that happens is when people normally perform feature selection, they directly apply it to their test set, and then they keep on trying to like overfit. You can like overfit your whole feature selection process on the specific error you get on a test set. And so there's some inherent bias if you were to always perform it on the same exact set, test set. So it's important that like as a scientist, again, when you come in and you're trying to find like what features work best for your model, that you still hold off one set of data that you ultimately test on once you do all this feature selection on some other data. So if the point is that you want to completely decouple that one process from your final evaluation of the model, only because you can easily kind of bias your methods to particularly fit to that one type of data. Does that sort of make sense? The whole point is that you guys should all just be very careful on how you kind of ultimately evaluate this, because there are subtle biases that could be kind of underlying your processes.
Yeah.
So just keep that in mind.
And to respond to Shuming's question a bit, so like honestly, like in practice, the words feature selection and feature extraction, which is what like PCA and TSNE and stuff like that are, they're not like super well defined, but like basically like the most important distinction between them that people often get wrong is that feature selection does not transform your features themselves. So it just selects a subset of your features to use in your model. The feature extraction reduces the dimensionality by transforming your features into like features that are more representative. So it would consist of like, you know, like a linear transformation of your feature space instead of just selecting some features that work the best.
Right. Oh yeah, so now we'll just jump straight into dimensionality reduction. So right, so as Jim was saying earlier, like there's a lot of problems when you have large dimensional data, because as you said, the curse of dimensionality, you need an exponentially more amount of data points to kind of really understand the inherent distribution of your data, especially when there's a large dimension. So it's almost always in your best interest to try to re-express the same amount of information in a lower amount of dimensions or in a lower amount of degrees of freedom. And so that's sort of the whole reason why feature engineering exists, right? You want to sort of minimize the dimensionality while maximizing the kind of inherent information that's being expressed. And so there's two kind of models that we want, or two kind of methods of feature extraction that we want to go into, that we find really important. And yeah, I guess in general, these are something. So the cool thing about neural networks is that they kind of figure out all this stuff for you. Because of all these inherent nonlinearities that exist inside of the neural network, it kind of does this feature engineering for you, because it tries to find how it can transform your initial data. And it does all these random transformations in all these layers. And then it tries to re-express your information in such a way that at the very last step of the neural network, it just does a straight linear regression on the transformed data. So another way of thinking about neural networks is like literally as having your input data, and you are not doing any work to actually engineer in any way, but the neural network does all these crazy transformations such that in the last layer, it applies linear regression on that automatically transformed data, if that makes sense. So that's a cool part about neural networks. And there's a lot of different subcategories of neural networks and how it extracts features in different ways. But I think that the two main things that we're going to talk about are really PCA and t-SNE. Yeah, so I mean, just going back, this is just like a general introduction to it. I guess we can go straight into the two different ones, and then you guys can ask questions then.
Oh, I just wanted to mention something about feature extraction.
Yeah.
So like one, like Anish said, the reduction in dimensionality is really important. But also like even if you have like really sophisticated techniques, there's like other benefits that feature extraction can have. So for example, if you were trying to do like transfer learning, which is where like you use kind of one model, or like as a concrete example, let's take BERT, right? So basically what that did was it took a really big model to learn representations of words. And then that representation of a word basically, or the vector that captures that word or that sentence, basically just captures the meaning of the English language. So now that you took that like feature extracted representation, you can apply it to a bunch of different models and you don't have to retrain that feature extraction. So this can be really powerful if you want to just like train one thing and then use that one thing to apply to a bunch of different tasks. So it's not only for reducing dimensionality, there's also a lot of like very powerful things that you could do with this.
That's very true. Yeah. In fact, I think we had a project last semester actually that worked with BERT a lot, right? I think it was called Inspector, and they worked a lot with BERT. So a lot of the projects might actually start using some of these really cool models. Cool. Okay. So then just to jump straight into PCA. So like PCA is like one of those things. So like I've probably learned PCA in like 4 different classes at Berkeley. And like, it's kind of insane how you kind of get a different perspective on it every single time. Like you'll learn it in 4 different ways in random classes that you might take. But at a very high level, you essentially try to kind of, you have your data set and you try to re-express your data in a different basis. So what that means is you try to, like, given, like, let's say we're plotting these points right here on the top right, and this is our data set. So like traditionally you could specify this by like 2 points, right? Like if this point right here is like what, 0 and 0, right? So like this middle point would be 0, 0, whatever. Or let's choose a different point actually, like 4 and 5. Like that's how you'd specify this point right here. But another way of expressing that same exact point is by using these 2 coordinate axes, right? And so suddenly like this point will be whatever the distance is from here to here, and whatever the distance is from here to like whatever, the y, or the second component is, right? So fundamentally the data is exactly the same, but you're just kind of you're just choosing a new coordinate system that kind of makes that kind of makes your life easier. So what does it mean to kind of choose a new coordinate system? well, there are certain like constraints that we want to ensure that these coordinate systems actually makes your life easier. And it turns out that we want to kind of make sure that every single axis or dimension, quote unquote, maximizes variance. And what that means is you kind of like, it kind of naturally holds that you really want to, in order to kind of understand how your data spread, you want to kind of find an axis that kind of encapsulates the most spread of the data, right? So if you see like the first dimension, like you'll see that a lot of the data is spread along that first dimension. And so that becomes a very valuable dimension, or like a new axis to express your data from, because suddenly like I have a whole range of values that I can associate with very specific points. And so like, again, you're not really fundamentally changing the data, you're just kind of fundamentally changing the axis with which you represent the data. And the metric we're using is how this new axis, how it encapsulates the spread of information along that direction. And so like that's sort of me putting into words what exactly the math behind PCA does. And I would highly encourage either like paying attention in class when they talk about whatever, I think they go over like 16b, also EE16b. And if you're really interested in the math of it, there's definitely a lot of cool, useful resources online. But again, so like now we have a way of kind of re-expressing our information in different, more useful axes. And so what can we do with that, right? So as Jim was saying, right, like we want sort of a way to also reduce the dimension of data, right? So suddenly, like imagine you have like a 100-dimensional vector, and let's just say like the last 50 dimensions were kind of just like, were very low variance dimensions, meaning that like there were kind of points that existed, but they were all very densely packed around the same value for the last 50. But maybe in the top 50 features, like there was a lot of variance, right? So when you perform PCA on this data set with 100 dimensions, it could be the case that the first 50 the first 50 dimensions after running PCA actually really encapsulate all the spread of the data, but the last 50 don't actually really encapsulate much of the spread. So like to like, then you kind of can make a decision being like, I want to cut off the last 50 dimensions, right? Like to me, that stuff's not very useful in terms of being able to differentiate these random points. And so that's kind of the point, right? Like we want to re-express it in a different coordinate system, and then kind of cut off the dimensions that don't seem to have a very large variance, right? Because that's not very useful to us. And so this is sort of a way for us to reduce dimension of our data set. And so yeah, like looking at these graphics, like right, like if you see here, this is a 3-dimensional thing, but it seems like there's like a plane, a 2D plane in which most of the information is spread, and that 2-dimensional embedding looks like this, right? So suddenly using 2 coordinate axes, you can express 3-dimensional data while still maintaining all this useful information. And again, this is very important. So if anyone has questions, please feel free to ask. Because I know I was definitely very confused when I was first introduced to this. So does everything sort of make sense?
So
yeah,
I just want to understand if like
yeah,
my understanding makes sense. So basically, what we're trying to do here is we're first rotating the axes, and along the axis such that the first dimension has maximum variance, and then after that we the rest of the axes also we keep on rotating and rotating, and we get rid of the axes that have the least variance. Is that what we're doing?
Right. So there's a subtle, like it's not quite rotating, but it is definitely a form of just finding the correct axes. I guess you could say it's a rotation because they're all orthogonal at the end of the day. Jim, would you say it's probably a rotation then, I guess?
Yeah, I think there's a special like term for that kind of rotation. I forgot what it was.
Or like an
You
orthonormal.
multiply by a matrix, right, to like rotate it basically.
Yeah,
Yeah.
I guess because they're orthogonal, I guess you could consider it a rotation. Although that actually brings up a good point. It would only be a rotation if it's like zero meaned, and as long as it's zero meaned. Otherwise, you would need like some sort of affine transformation to ensure that it goes in the right direction. But for the most part, I think for simplicity of thought, yeah, it's essentially just like a rotation of your coordinate axes such that the first dimension is in the maximal variance. And it turns out that every other dimension that you add, like for example, the second dimension is gonna have to be orthogonal or perpendicular to the first dimension. Because if you think about it, like if the second dimension was at all not orthogonal to it, then you're kind of just kind of redundant information, right? Orthogonal, when it's orthogonal, that means you can explain everything that's not directly explained by the first dimension. So
Right.
as you were saying, yeah, it's sort of like a rotation. And then you kind of cut off the last dimensions that have very low variance, only because, again, as you sort of mentioned, like we don't really care about the stuff that doesn't really explain a lot of things. We only care about the stuff that explains all of the spread.
Okay. Thank you.
Yeah. Does that sort of make sense? Yeah. If anyone has any more questions, feel free to ask. But again, yeah, just at a high level, this is very important when we want to kind of choose which features we feel like are most representative of the actual spread of information. So it's really useful. And again, I think you'll learn a lot about this in your classes, but again, feel free to reach out or read on online. Okay, now TSNE is like a whole different beast, because TSNE is not a linear model, or it's not a linear like method. So PCA is cool because it's a linear method, so you can kind of express it as, you know, matrices and all the common linear algebra talk that we know so well. So TSNE, for example, is actually like a non-linear optimization method. So now we're kind of turning the dimensionality reduction problem into something that involves optimization and some non-linear techniques. And so we'll actually get to get our hands dirty with PCA and TSNE in the workbook that we'll probably be doing in the next 10 minutes or so. But what really happens is, like, if you have very, very high dimensional data, there is inherent distribution of points in a high dimensional data space, right? So let's say we have like 1,000 dimensional space, you have an inherent distribution of points, right? What TSNE tries to do is it tries to kind of mimic or make as similar as possible that distribution of points, but in a lower dimensional space. So like and the way that you can kind of quantify a distribution is by entropy. And I don't know if you all probably heard of entropy yet, and there might be another lecture series on that, or maybe not, but entropy in theory is kind of just the measure of how chaotic your distribution is, or how predictable your distribution is. So if something is like 50-50, like, or if the distribution is like uniform, right? A good way that's a very high entropy, because you have like it's very hard to determine what the next outcome is going to be, because everything is so probable, right? But let's say the distribution was like, okay, it's like it's like there's a right tail or right skewed or whatever, then you know that like with high probability, the point that you're going to that the outcome of that distribution is very heavily most likely going to be on the left side. So now you have a better understanding of what the outcome is going to be. So there's less entropy. So entropy, again, is like a measure of kind of like how chaotic your distribution is. And there's a lot of like random metrics you can use to quantify these distributions. And so what you do is you kind of compute the entropy of this very high dimensional data distribution, and then you kind of have a lower dimensional representation of that same distribution, but then you kind of try to match the two entropies in the higher dimensional and the lower dimensional space. And so suddenly the problem becomes, what is the most optimal kind of configuration of lower dimensional points such that the entropy of the two distributions is most similar? And so that's inherently an optimization problem, right? We're trying to find the most optimal kind of expression of the dimension of the data in lower dimension that most matches the entropy in the higher dimension, in the higher dimensional thing. So again, this is like inherently an optimization dimensionality reduction problem. And as the slides state, there's a lot of cool math that's involved in TSNE, but yeah, like it can also be analogous to the similarity between points. I think it tries to like mimic the pairwise distances between points, and it tries to make it all proportional in the higher and lower dimensions. And so yeah, just by virtue of it being an optimization problem and not like a linear method like PCA, it does require iterative optimizations. So it is definitely more computationally expensive. But TSNE is really cool because it really, like as mentioned here, like it works on a lot of cool data sets, like genomic data, NLP stuff, images, like things that are very inherently complicated in terms of the distribution in higher dimensional data. Okay, so with that, is there any questions? I know that's kind of a high level view of it, but I feel like it's just important to kind of know where it comes from, because you'll see that you have a lot of the times you have the option of just plugging and chugging your data into a t-SNE optimization method, and it's spitting out a proper lower dimensional expression of the same data. But it's good to kind of understand the fundamental differences of it. Does anyone have any questions on that?
So what does it mean that like the data is inherently in some distribution?
Yeah, so I mean, if you even look right here on the right, this looks like it's the reduction. This is like the result of t-SNE, but like you can inherently see like this is the distribution of your data points with respect to these two dimensions, right? So like you can imagine, like, yeah, when I mean distribution, I kind of mean like just like the inherent, I guess distribution in this case, you can kind of think of it as like the pairwise distances between points. Like I guess in this specific case, like that's one thing that t-SNE ends up also kind of preserving, is like ensuring that the relative distances between points in the specific expression of features is still maintained. So like just, yeah, when you think of distribution of points in a space, just kind of think of like just the inherent relationship between one and all the others. If that makes
I
sense.
think it's like just like overall like a really abstract like concept. When you think of like, you can think of like a distribution of like images of human faces, which would be like, I guess, what does like the set of all human faces look like, and like what are like, how do pixel values sort of how are the pixel values distributed in that like set of human faces, if you're like talking about a distribution of like human faces, right? And so when we when we have like a data set, right, that's sort of a sample from the overall distribution that you want to model, right? So for human, like I guess specifically for like face of humans, right, the overall like the set of all human images or like human faces is like, I mean, is insane to think about, but like you have this, I guess, you have like a data set which is like a sample from the overall distribution, and you try to like learn, you can try to learn what the overall like distribution looks like. And what like this method does is it like tries to I guess lower the dimensionality while also preserving, yeah, like Anish was saying, preserving like pairwise distance between points.
Right, and
Yeah.
just to be a little bit more clear from what I was saying earlier, I think that the distribution whose entropy you're trying to match is fundamentally proportional. Like it kind of encapsulates the information of pairwise distances between points. So like when you consider this distribution that you're matching, the distribution inherently is of like if you if you sample a specific point, it'll tell you kind of the like, okay, I actually don't know too much of the math behind it, but I feel like when I first learned this, it was essentially saying that the distribution itself kind of encapsulates all the information of all the pairwise distances of the points, which is exactly what you kind of want to match in a lower dimensional setting. So like, yeah, again, at a high level, I think, as Alexia also said, it's kind of abstract to think about, but the fact that it is an optimization problem and there's an iteration involved, and like it'll sort of figure out what the most optimal like low rank understanding of it is, that's kind of, I think, the extent to which is useful.
KL divergences again?
Yeah, so KL divergence, it's a whole entropy cross entropy. So when you kind of want to quote unquote match entropies, KL divergence is essentially like the difference between the entropies. So you want to minimize the difference between the entropies, which is KL divergence. Yeah, honestly, I feel like the Wikipedia article on this does a very good job on like really making it very mathematically sound. So if you want to just skim the Wikipedia page, I feel like that's a good intro to how it works. I think that stuff will sort of make more sense. But yeah, we definitely didn't want to get too super detailed on the math behind it.
Yeah, I think probably like the mathematical side is not as important as like
Right.
learning, I guess, what it does in practice for this case.
All right, cool. Yeah. Any more questions before I think we jump straight into the notebook? Okay, let me stop sharing my screen, and then let me send you the notebook.